Welcome back, students. In our last explainer, we kicked things off with part 1 of the periodic classification of elements. We looked at those early, kind of limited attempts. Remember Dobereiner's triads and Newland's law of octaves? Well, they were a great start, but today, in part 2 of our Chapter 5 journey, we're diving into a real game changer. We're going to meet the mastermind who finally brought true order to the elemental universe.
Seriously, how do you organize absolute chaos? Think about the scientific landscape back then. After Dobereiner and Newlands hit dead ends, scientists were basically staring at a massive, chaotic puzzle of elements. They desperately needed a system to make sense of the whole shebang. Imagine having all the pieces of the universe scattered across your desk, but with zero instructions and no picture on the box. How on earth do you turn that mess into a predictive tool?
Okay, let's quickly glance at our roadmap for today's explainer. We've got the father of order, Mendeleev's periodic law, designing the table, the genius of gaps, flaws in the design, and we'll wrap it all up with a quick revision summary.
Section 1. The Father of Order. Let's meet the brilliant mind who decided to tackle this giant elemental puzzle.
Enter Dmitry Ivanovich Mendeleev, a highly brilliant Russian chemist. You'll often hear Mendeleev celebrated as the father of the periodic table, and honestly, he completely earned that title. He didn't just casually group a few elements together. He gave us the very first widely accepted comprehensive system. He essentially laid down the absolute foundation of modern chemistry, making the study of these elements so much easier.
Section 2. Mendeleev's periodic law. Because, every architect absolutely needs a solid blueprint.
Mendeleev's entire blueprint was built on this one critical statement, which we now call Mendeleev's periodic law. He arranged all the known elements in increasing order of their atomic mass and noticed a profound pattern. He stated that the physical and chemical properties of elements are periodic functions of their atomic masses. This single sentence literally became the guiding principle of chemistry for decades.
Let's translate that scientific jargon a bit, right? Periodicity simply means that when you line up the elements from lightest to heaviest, you start seeing the exact same chemical behaviors repeating over and over again. It's kind of like the keys on a piano. As you move up the keyboard, the pitch gets higher, but the actual notes, A, B, C, they repeat at regular intervals. That's periodicity in a nutshell.
Moving on to Section 3, designing the table. Let's see how his law actually translates into a physical grid.
Mendeleev basically used 3 main pillars to classify everything. First, increasing atomic mass. Second, grouping by similar chemical properties. And third, looking super closely at the chemical formula, specifically how elements reacted with oxygen and hydrogen to form oxides and hydrides. But hey, keep a close eye on that very first rule about increasing atomic mass. As we'll see a bit later, he actually ends up cleverly breaking his own rule.
So here is the brilliant grid structure he came up with. He created 7 horizontal rows, which he called periods, and 8 vertical columns, known as groups. And he even divided each of those groups further into subgroups A and B. The true magic of this grid? Any elements that land in the same vertical group share strikingly similar chemical properties.
Let's look at a concrete example so you can see this in action. Take lithium, sodium, and potassium. Because they share the exact same chemical properties, they're all metals and they all react wildly, sometimes explosively with water, Mendeleev logically locked them into the exact same vertical group. Just by knowing its group, you instantly know how the element is going to behave.
Section 4. The genius of gaps. This is where Mendeleev goes from being just smart to an absolute genius.
What's truly fascinating here is that Mendeleev deliberately left blank spaces in his table. He didn't just force elements to fit where they clearly didn't belong to make his chart look neat and tidy. It's exactly like leaving an empty chair at a dinner table because you absolutely know a guest is arriving late, even if you haven't actually met them yet. He trusted his law of periodicity so deeply that he knew these missing elements just had to exist out there in nature.
And get this, he didn't just leave the seats empty. He actually predicted what those late guests would be like. He predicted the existence and the specific properties of undiscovered elements he temporarily named Eka-aluminium and Eka-silicon. And guess what? Years later, scientists actually discovered gallium and germanium, and their real-world properties matched Mendeleev's bold predictions almost perfectly. Mind-blowing, right? This was the exact moment the scientific world realized his table was a highly powerful predictive tool. So, to sum up his massive wins, the merits of Mendeleev's table are just immense. First off, systematic classification. Elements with similar properties were finally grouped together, making chemistry way easier to study. Second, his bold prediction of new elements like gallium and germanium. Third, he actually used his table to correct the faulty atomic masses of some existing elements. And finally, the design was so incredibly robust that when unreactive noble gases were discovered much later, they just slid right into a brand new, separate group without disturbing the rest of the table at all.
Section 5, Flaws in the Design. Because as we know, no early prototype is completely flawless. Despite its huge success, scientists eventually started noticing some cracks in the foundation. There were 3 major drawbacks, limitations that simply arranging elements by atomic mass couldn't resolve. Let's break those down. First up, the uncertain position of hydrogen. Hydrogen was basically a total mystery guest. On one hand, it acts like an alkali metal because it has one valence electron. But on the other hand, it exists as a diatomic molecule, exactly like the halogens. Because it perfectly mimics both groups, deciding its actual permanent position on the table was basically just a guessing game.
Second limitation, isotopes. Now, isotopes are atoms of the exact same element. Take hydrogen's variations, for example, protium, deuterium, and tritium, but they have totally different atomic masses. Since Mendeleev's entire table was built strictly on increasing atomic mass, there was just no logical place to put them. I mean, if you sort strictly by mass, every isotope would need its own separate box, but chemically, they're the exact same element.
And third, anomalous pairs of elements. Remember earlier when I said he'd break his own rules? Look at cobalt and nickel. He placed cobalt, which has a heavier mass of 58.9, before nickel, which is lighter at 58.7. He blatantly ignored his own increasing mass rule just so their chemical properties would properly align in the correct vertical groups. He knew the chemical properties mattered more, even if his atomic mass math didn't quite add up. We see the exact same anomaly with tellurium and iodine.
Section 6, Quick Revision Summary. Let's pull all these amazing puzzle pieces together.
Okay, if you're taking notes for your exams, these are your absolute must-knows from today's explainer. First, be able to state Mendeleev's periodic law perfectly. Properties are periodic functions of their atomic masses. Second, know exactly why he's the father of the table, because he gave us the first widely accepted systematic classification. And finally, be ready to list those key limitations, especially that tricky, uncertain position of hydrogen. Mendeleev's work was without a doubt a world-changing milestone. He successfully brought order to absolute chaos. But those lingering flaws, the isotopes, the heavy before light swaps, well, they kind of prove that atomic mass wasn't the flawless foundation he thought it was. Which leaves us with a massive question. If atomic mass is wrong, what is the real secret hidden inside the atom? Keep that thought in your head, because that is exactly what we'll be decoding in our next explainer as we discover the modern periodic table.